Hey all listeners, let's see this question of Irodov. It's from Hydrodynamics. It's question number 1.321. The question states, the horizontal bottom of a wide vessel with an ideal fluid has a round orifice of radius R1. This is R1. Over which a round closed cylinder is mounted whose radius R2 greater than R1 as shown in this figure. The clearance between the cylinder and the bottom of the vessel is very small. The fluid density is rho. Find the static pressure of the fluid and the clearance as a function of the distance r from the axis of the orifice. The height of the fluid is equal to h. Okay. So, this is the liquid height h. This is exposed to atmosphere and here liquid goes down. So, pressure here is PATM. And the pressure here would also be PATM. So at this section, immediately from the Torricelli's theorem, we can write this velocity. I can say that is a V1. So V1 will be directly, I can use square root of 2GH. This is one thing. In the question, we have to find the pressure inside this clearance. Find the static pressure and the clearance as a function of distance r from the axis. So this is the clearance. In this clearance, we have to find pressure as a function of distance from the axis. So suppose we take a general distance. Suppose we have to find pressure here. And this point is at a distance small r. Here we have to find pressure as a function of small r. So just let's try to visualize the clearance part. So clearance part, here let me try to draw a diagram. This is the clearance part. Clearance has a very small thickness T. And clearance ends here. So from the clearance, the fluid flows, and from here the fluid goes in the downward direction. So fluid flows in the radial direction, like this, like this, like this, like this, like this, like this. So inside the clearance, the fluid flows in the radially inward direction. And when it goes down, the radius has come down from R2 to R1. So now I want to draw the top view of this diagram. And when I will draw the top view, this T will not come. That will be just coincided with the upper top and the lower top. So with that thing, so if I draw the top view, so top view I am drawing just here, at here, from where all the fluid particle merges and goes down, and here. So I am drawing the top view here and here. This section. This is at radius r. So this is at radius small r and this is at radius r1. The fluid here is moving with, say, velocity v, like this, like this, like this, like this. This velocity at position r is v, and when it reaches to r1, the velocity has just become, so from here the velocity will be the same. Whatever velocity here has come basically same from here, that point. So at this point here, the velocity from here itself, the velocity has become v1, alright, and here the velocity is v. So this is v1. So we'll apply the continuity equation. Just think, this circumference is 2 pi r and there is a height t. So at this section, fluid is crossing through an area 2 pi r into t. Just imagine, this is a 2 pi r and there is this height is t. So this whole area, that whole area would be 2 pi r into t. And here the area would be 2 pi r1 into t. So applying continuity equation on this section and this section, we will get 2 pi small r t into v is equal to 2 pi capital R1 t into v1. So we'll get v1 by v, v1 by v, 2 pi and t will get cancelled. So v1 by v will be r by r1, and now we can apply Bernoulli theorem between these 2 points. These 2 points, this is 1 and this is 2, here and here we can apply Bernoulli theorem. So applying Bernoulli theorem, you can see this point is 1 minute. This is 1, this is 2. At point 1 pressure is P, and at point 2 pressure is P atm, because now it is exposed to atmosphere. So I can write, change the color. I can write, a minute. Yes. Oh, here. So P1 plus half rho V1 square is equal to P2. P2, 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 this P2, P2. This is now exposed to atmosphere. So here the pressure is P atm. Let me see. That will come in terms of atmospheric pressure. So that is a P atm plus P atm. P atm, let me write P atm as P naught plus half rho V square. So clearly this P1 is equal to P naught plus half rho V square minus V1 square. Half rho, a minute. So at point 1 pressure is P1, velocity is V. At point 2 pressure is P atm and velocity is V1. So I have to just 1 minute. Yes, and that will be corrected now. See clearly there should not be any confusion. This point P1, so pressure is P1, velocity is V. This point is 2. I have just write the numbering in a not very proper way, but okay, whatever it is, we will follow this. So at 1 velocity is V, pressure is P1. Here pressure is P1. At point 2 velocity is pressure is P atm, that is P naught. So now that should not be confusing. So that is V1. So V1 square minus V square, and then you can take V1 square common. So this will be rho V1 square by 2, 1 minus V square by V1 square, right? And then that is, see, that's just simply Torricelli's theorem. This is a large open tank and pressure is P naught, pressure is P naught. The only energy which are changing is kinetic energy and gravitational potential. So here the velocity would be directly root 2 gh. So V1 square is 2 gh. V1 square in place of V1 square is 2 gh. So that will come to be rho gh, and 1 minus 2 gh, 2 and 2 will get cancelled, and V1 by V is small r by r1. So V by V1 is small r1 square by small r square, and that will be our answer. Alright, like